in a post-common envelope system. Haha. Sorry, it just popped up and told me we're being recorded. Yeah. But what I wanted to put on this slide was some work I've started doing with the fantastic Backyard Worlds project. I know Jackie and Danny and Adam are here. I don't know if anybody else is. I'm looking at the list of names on the side. But Backyard Worlds uses a series of images from WISE, and we have citizen scientists who are looking for nearby brown dwarfs. And some of our super users who are sort of really got into the project and are interested in the science and not just sort of finding the objects have found a bunch of these that appear to be co-moving with white dwarfs. So we've got white dwarf parameters from Gaia, we've got brown dwarf parameters from WISE, and we are hoping that we can use the white dwarf to get the age for the system. And then we can put an age on the brown dwarf and use these as benchmark objects and sort of say, okay, well, we know this should be 2 gigayears, not 5. How does this compare to the models? And try and see if there are any trends also to do with like how these objects form, what sort of masses you're likely to get, what sort of separations, because brown dwarfs orbiting white dwarfs are weird at the best of times. And we still don't really know how the close ones form and which stars get them, let alone the wide ones. So I will stop there. But yeah, it's a really cool project. People should go have a look on Zooniverse at Backyard Worlds and some of the stuff that we're doing.
Great, that's awesome. Does anyone have any like comments or questions or? I don't know if I can see if people raise the hand when I'm in this view because I'm in presenter mode, so it's like
I can't see any hands up, and I don't think anybody other than Jackie saying Backyard Worlds for the win has added anything to the chat. So I think awesome. You're good to move on.
Okay, great. Thank you so much, Sarah. Okay, so checking. Oh, there's a hand up. Would you like to say something, or is that just a practice hand?
No, I was afraid it was too late already, so sorry for not having read everything properly. Is it just a single object for now? Or
we have about 20.
You're hoping to report?
Yeah, we have about 20 or so at the moment that we're in the process of confirming both the white dwarfs and the atmospheric composition and getting spectra of the brown dwarfs. So yeah, I think there are 6.
So you do have some parameters for this one already?
Yeah.
Okay.
Yeah, this one's one of the 7 I think that have been published to date in Aaron Meisner's paper.
Oh, I just looked that up. Then.
Yeah, there's two in that paper.
One of the 7 also. I look at the paper.
Great, we have a couple more hands up. Do you want to go if your hand is raised?
You should probably direct people. We appear in the order that
sorry, it doesn't
hands are raised.
Provide me my name. Yeah, Tom, sorry. You are.
Are you just using WISE combined with Spectra, or is this a multi-mission affair? Is it just the two components?
It's mainly the 2. So the Backyard Worlds project works on WISE images. And so this is where people are spotting 2 things that look like they're moving together. Generally, we can get the white dwarf out of Gaia. A lot of them are in the DR2 white dwarf catalog. Some of them aren't, depends on where they are in the sky. The brown dwarfs are pretty much never in Gaia. So you're then using the WISE parameters and any other wide field catalogs we can get hold of for colors and then eventually spectra. And I need to point out that in the many Adams on the team, I don't have Adam Bergesser on the list of observations. And Adam is one of the people that's done a ton of our spectral observing. So that was an oversight. I'm sorry, Adam.
Many Adams.
Cool, thanks.
ZJ, you've got your hand up.
Oh, yeah. Hi, Sarah. Yeah, so for the 20 White or Brown Dwarf like binaries or companion host systems, I wonder what is like the latest type of the companion you have found, and also what is like separation range for these companions?
So most of them are a thousand AU or so, slightly wider. So we have a few that are close to being unresolved on the WISE images, but a lot of them are properly wide. So, you know, sort of obviously massively separated, a few arc seconds. Most of these are early L. We do have a couple that are, I think, T dwarfs that need following up, but most are early Ls, which is quite interesting because I think there's only one of the published objects that are L dwarfs. Most of the 7 that are known are all T dwarfs. So the fact that we're finding a bunch of L dwarfs is actually pretty interesting.
And there's another hand up. It doesn't give me the name of you if your video is on, and so I apologize.
It's Josh.
Yeah, it should be me. Hey, Sarah, how's it going?
Hey, I'm all right.
I had a question about how well you can get the age of the white dwarf when you start to think about comparing them to evolution models. And is there any worry that maybe the brown dwarf and white dwarf interacted to maybe complicate the picture of the age of the species? Like flung it out.
Yeah, no, I'm with you. So yeah, the answers are sort of, it depends and it depends. In terms of interaction, because they're really wide, it's unlikely there's been any sort of actual interaction. The brown dwarf may have been pushed wider as the white dwarf formed. So you have your giant, it gets rid of its envelope, and at some point that envelope forms its beautiful planetary nebula, and it's perhaps shoved the brown dwarf out. And at that point, the brown dwarf may have been exposed to some sort of wind, but there's not a lot of stuff in these envelopes and they go out over quite a large area. So we don't think the brown dwarf is likely to have been significantly affected by anything like that, and certainly not a 1,000 or so AU. In terms of the age, it very much depends on the white dwarf. So sometimes we have kinematics to help us. If the kinematics show it's likely to be thick disk or halo or something like that, then we have a good guess. And if most of the white dwarfs are bog standard white dwarf, 0.6 solar mass, average mass, this means we can actually use something like an initial final mass relation to get an initial mass and work it back. And that's quite reliable. The problem is if the white dwarf is super cool, and a lot of the published ones are, so WD 806 minus 661 is probably the famous one of these, and it's in everybody's GTO James Webb proposals for this planetary mass thing that's super wide with a white dwarf. But the white dwarf is what we call a DC white dwarf. It's completely featureless. It's just a black body spectrum. And if you have that, that's more difficult because you can get the temperature from your black body model, but you can't really get the gravity. So then you have to sort of assume a mass or work from a luminosity and a mass radius relation. So things can become more complicated then if the white dwarf is featureless. But if the white dwarf is a normal DA hydrogen-rich white dwarf, then yeah, you're pretty good.
Awesome, thank you.
Great, thank you so much, Sarah. All right, we'll move on so that everyone can have an opportunity with the slides. That was great. Okay, so I am also on the observational side. So this is actually my slide. And this was one of the objects that I have been investigating for a while now. That was one of the main motivators for, at least for me, to propose this kind of discussion. So this object, HT4113C, is actually the brown dwarf. So it is a brown dwarf companion. And it's in a system that, so on the upper right there, you can see there's the primary star. And then it also has a very widely separated stellar component that's like 45 arc minutes away, so pretty far away. But then we also have a highly eccentric inner planet that's been observed through radial velocity. So you can see the radial velocity curve in the bottom right there. So you see this very eccentric inner planet. And then we also directly imaged this companion, the wider companion, which is at about 500 milliarc seconds. And so this was first published by Anthony Cheetham in 2018. So we have observations that go back to about 2016, and then have been following this up. So when this was published, it was the spectral type kind of puts it at a very, very late T-type or potentially an early Y-type brown dwarf. And so you can see these models, the plot from Anthony's paper there, where we can't necessarily differentiate whether it's like 500 or 600 Kelvin and sort of within this regime. So these are sphere observations, and this is across the IFS and the H2 and H3 bands. So what we're kind of hoping that we can do, fingers crossed, we get JWST time, is we can go towards those longer wavelengths and look in the sort of more mid-infrared range with NIRCam, and this will be able to actually help us differentiate what we're looking at. So again, this is a pretty like sort of interesting object in the sense that it's very much a benchmark brown dwarf. We have a mass estimate from the primary star. We have an age estimate from the primary star. And then we also have the dynamical mass. So this is one of the questions as well. It wasn't just about the spectral type, but the dynamical mass, which we get from combining the radial velocity information with the relative astrometry from the images, gives us about a mass of about 66 Jupiter masses. But when we actually look at the isochronal mass, and that's from the COND models, and at least this is from Anthony's paper, this gives us about 30 Jupiter masses. So one of the hypotheses we have is that maybe we're looking at a compact, unresolved binary system, like two brown dwarfs orbiting one another. So instead of us just looking at this one sort of brown dwarf companion, maybe we're looking at an unresolved compact binary brown dwarf. So I think this is a pretty interesting system. And hopefully in the future, some JWST observations will help us answer some of these questions. Yeah. I see a couple of hands raised. And again, I can't see your names because I don't know what's happening with my view, so.
Oh, I just raised my hand. I'm ZJ.
Yeah.
ZJ. So yes, it's very interesting finding. And also I noticed as you mentioned, the dynamical mass is much higher, or factor 2 in this case, than the mass derived based on the age of the host star. And in the meanwhile, we do know there's a growing list of the very massive like T dwarfs.
Yes.
And I just wonder, like, what is our current understanding of this kind of mass inconsistency? Or on the other hand, it could be understood, I mean, we could understand it like by alternative ways, like given the mass and age of the system, the luminosity predicted by the models are over predicted, right, for these companions. And that means we will need some inefficient heat transfer from the core, or some less opacity in the atmospheres. And both of this, I sort of feel is not very consistent with my understanding of the development of the current models. So yeah, so it's like there are many questions in my head, and what's your understanding on this?
Yeah, I think I have the same kind of questions in my head, and I'm kind of hoping that maybe members of the community here might know the answers better than I do. But yeah, I think the sense that the luminosity is over predicted in these it is probably accurate. I see many hands raised, so I'm gonna let some other people chime in as well.
Yeah, of course.
Emily, I'll help you moderate questions. So Laura
Thank you. Thanks, because I can't see the names and I feel really bad and I don't know. Thank you.
Go ahead, Laura.
Hi. So I was just wondering, I mean, you say you have the isochronal mass, but how accurate do you think the age of the star, and could the uncertainties just be due to, I mean, how was that found? How was the age of the star found, and what are the uncertainties on that?
Yeah, so the eight, like it's definitely like the biggest uncertainty here, right? And so we have to kind of take the age with a pinch of salt in that sense. So the age comes from, yeah, like, I guess ultimately the age also comes from stellar isochrones. So there's definitely uncertainty in that, and we have to allow for that. But I think even with that uncertainty, you still end up with a large factor where it doesn't completely, like, yeah, agree with the dynamical mass. And yeah.
Yeah, this is Mark Marley. It can't, at least the models would say at that mass, it doesn't get down to 600 Kelvin in the age of the universe. So something would have to be really off.
Yeah, and I think, yeah, I don't think anyone is trying to argue that it maybe is like this, but it's just that this is what it's giving us, and there's clearly something off here. And I think I guess the details are in the model is what I would say as an observer, of course, but yeah.
Elena?
Yeah, Emily, so I have a question. So this discrepancy between with the masses estimates only happens for the late T's or also for the early T's, or there is no, we don't know?
So my understanding is that mid to late T's suffer the most with this. So then there's also the uncertainty at the whole LT transition as well, which is a different kettle of fish. But yeah, so there are a handful of objects around like the mid to late T's where this is the case. This is not the only object like this for sure.
No, it's not, but it's interesting that there is also, it doesn't happen in all the T's, but just, the later mid to late T's.
Right, yeah, because I published a mid T type Brown Dwarf last year that completely agreed with the models and was like, oh, okay, well, this is awesome. So yeah, it's not all, but it is some. So clearly something is happening, yeah.
Elena, I'm sorry, Emily, do we have time for more questions? I don't know what our time is.
Yeah, I was going to say, let's move on so that we have time for others too.
So, or Daniela, Derek, if you want to type your question into the chat, maybe Emily can respond to you in the chat.
Great.
Or maybe in the Slack so we can retain it.
Oh, probably Slack might be.
Oh yeah, Slack. Okay, thank you. Okay, next up, Eileen.
Okay, so I just have a cautionary retrievals tale. So part of my thesis sample, I was looking at this variable object, J1539. I ended up kind of slipping in accidentally as a comparison to the primary and the subdwarf binary J1416A and B. So this was a comparison to the primary. And I was trying to look at how do pressure temperature profiles of objects of similar effective temperature to compare to one another. And this was a really shocking result because this object is variable and we think its variability is due to clouds. But from the retrieval, it's telling us that this is a cloud-free object. But piecing together the individual and pieces of information you get out, you can come to the conclusion that it probably isn't cloud-free. So I'm showing the PT profile in the first plot. And what we're seeing is it's turning to become isothermal. And this is something I've typically seen when the retrieval is going to be better fit by a cloud model. Every cloud-free kind of turns down, you put a cloud in, and it's doing a better job. But because of the data we have and the additional parameters that go into the model with the cloud, it rejects it based on that. If we look at the maximum likelihood for the cloud models, it's fitting it better, but the extra parameters are justified with the data that we have. When you look at the spectrum of the object, so we have the spectrum in black, and then I'm showing grid models as purple and blue, we're seeing that the cloudy grid model is fitting the object better than the cloud-free ones. And then from the retrieval, we're looking at the iron hydride abundance in blue. So our retrieved value is the solid line with the shading. And what we're comparing it to is what we expect to get from a solar metallicity model grid. And we're finding that the abundance we retrieve for iron hydride is less than the maximum possible we expect to be in the photosphere. So it's likely that iron is condensed out and it probably should be a cloud. So this is a trend I'm seeing for a few objects. This one is pretty strong because it is a variable object. I'm seeing it with others, but it's really pointing towards we need more than near infrared data to constrain cloud properties. And it's going to be really important to get that mid infrared data, particularly for variable objects. And we're seeing it just for run-of-the-mill field objects as well. It's completely changing the shape of the PT profile, and things are starting to agree more with the models. So this is my cautionary tale.
Great, thank you so much, Harleen. Do we have any comments, questions?
Laura?
Yeah, if no one else has a question, I didn't want to ask too many, but what, I mean, would hypothetically high resolution spectra help? And I mean, maybe not for this object, but just in general. Coming from an exoplanet point of view, I know that can help, but I don't know if that would work for brown dwarfs. So I'm just curious.
So the problem for retrievals is you need to have 10 times the resolution of your spectra to generate that model. And we're running into a computational problem right now to use higher resolution data. Okay. So that's kind of the wall we're hitting. So right now we're just using low resolution specs data for these objects.
Okay, cool, thank you.
Adam Burgesser?
Yeah, I just looked really quickly at the spectrum of this, and it's definitely an unusually blue L dwarf. And I wonder if the variability is because the clouds are thin, and maybe that's, you know, that might produce more variability than you expect for thick clouds. So you may just not be sensitive to the thickness of the clouds.
That that could be a possibility. I don't think I've tested any other objects right now like that. So that's something I'll look into.
Did you have another question, Laura, or is that, no, just checking. Okay, great. All right, awesome. Let's move on to the next slide. So Eson, if I'm saying your name correctly, I hope if you would like to unmute yourself.
Yes, thank you, Emily. So yeah, following Emily's talk about slide discussion about HD 4113C and ultra cool dwarf. So one main challenge, as you see in the top left panel in the table, there are like several objects, cool objects, that their mass is not very clear. Their mass can be like something like Gliese 229b. It can be like between 30 to, I don't know, 55, 60, 70. So there is uncertainty, and this uncertainty comes from the fact that in modeling their atmosphere in evolution models, there is degeneracy between gravity, temperature, mass, and age. So there is this 4D, 5D space, which they're like all degenerate together. So what I did with Mark Marley and others, we asked this question, that whether we can use lithium not as an atom, but as a molecule. So first of all, lithium is a famous element. People are using lithium tests to see whether to distinguish between brown dwarf and low mass stars. So at low temperatures, although lithium changed to molecular lithium like LiCl, LiF, and LiH, mostly LiF and LiCl. So if you look at the top right flux here, you see the difference, the impact, or the comparison between flux on and flux off here. So for example, for LiCl at different temperature, at like T effective temperature of 500, you can't detect LiCl, but as you go higher in the temperature, like about 1500 to 2400, you can see LiCl, and it's the same as LiF. So we we are proposing to use LICL as an indicator and say that in the lac, if there is no detection of LICL at about 14 to 18 wavelength at micron, that could lead to a higher, to a larger mass. Yeah, this is pretty much what we are working on regarding using these lithium species to kind of distinguish between different masses for low ultra cool dwarfs.
Awesome. Yeah, I mean, this is, yeah, kind of addresses, like you say, some of the issues with the brown dwarf that I was presenting before. Kim, would you like to ask a question?
Sure. This is really nice work, Ehsan. I think it's really exciting to use lithium, like to see the molecular lithium used in this way. And I was just curious, do you think that the atmospheric variability of brown dwarfs in this range would lead to differences in like the strength of these molecular features, or is that something to consider?
Well, so if you look at the this, so on the left panel, the colorful plot is the lithium phase diagram. And the blue, for example, so you see pressure versus temperature. And at high temperature, you see atomic lithium, which is yellow area. But when you go up when you have lower temperature, you see the green and the blue area, which are LICL and LIOH, they formed. And then you see LIF. So to address your question, it depends at different layers of the atmosphere and at different effective temperatures, which you see the PT profile here from 1000 Kelvin, effective temperature of 1000 Kelvin to 2400, different form of lithium bearing molecules are expected to form in the atmosphere. So yes, the variability, and this is not only, so here we have cloud model on our modeling, but also we have cloud free, and we have different surface gravities, which again, different gravity and crowd free model, they all impact the lithium, like the signature, the spectral feature. But the main question for you guys as an observer, what is your opinion about like what is the chance to detect LICL, LIF, which they are like on the bright side of the spectrum, or I don't know how much like is the sensitivity, the signal to noise. This is something that I would like to hear from you guys.
Adam, I don't know if you want to address that question or if you have a different.
I have a different one, so if someone wants to answer that, I'm happy to defer.
Sorry, what was the question?
There isn't a question yet. We were waiting to see if anyone wanted to answer your question. But so I think it's worth reposting your question in the Slack, Ehsan, to see so people can ponder it. And so let's hear what the other thing Adam wants to ask.
Yeah, this is really cool, Ehsan, and I think perfectly timed for Davis T. I was wondering, you looked like you tried both cloudy and non-cloudy models. Did you see a difference in the detection of the lithium molecules between those two sets of models?
Yeah, there is some differences for atomic lithium at about 1000 to 1500. There is a big difference, like the impact of, so the presence of clouds will suppress the atomic lithium which this is something like we expected. For molecular lithium, like LiCl and LiF, again, there is some impact, but it's not that noticeable.
That's great to hear.
Thank you.
Great, thank you so much. Yeah, and we can obviously keep the discussion going in the Slack channel as well. So let's go to the next one. So this one is Dino, if you'd like to unmute yourself.
Thanks, Emily. So I'm Dino. I'm a graduate student at UC San Diego, working with Adam Bergasser, and just want to show, actually, we need some update opacities for near infrared high resolution spectrum. So the left panel is to demonstrate the J-band near spectrum in black compared to two different model grids. I'm using a MCMC for modeling framework to infer. So effect temperature, surface gravity, RV and V psi I, and the BD cell models in blue, and Serona model is in orange, yellow. So you see there's like a major, some major line differences around, say, 1.305 or 06 each micron, and 1.315 ish. So because of this opacity difference, and you can have a slight difference in RV and more significant in V psi I. And the inferred prices are very different, although these two models have different assumptions. But if you don't have such correction, and you have a very offsetted, not so statistically significant overestimated V psi I, if you look at the right panel, just to compare the BD settle V psi I compared to Serona, and typically because of the missing opacities, and if you just use a BD cell model and you almost overestimate the V psi I, and you see this kind of statistical trend that's in the T-Dwarf survey in individual near spectrum that I'm compared to. And we also see that in issue in H-band data. So the missing opacities is anhydride. That's kind of significant after 1.58 micron. And we also saw some improvements, actually much better by Serona models, where other models can't really do that. Although Serona models can go up to 2400 kelvins. So so we really need a higher temperature and updated opacity synthetic model grid to derive these kind of precise set of parameters. I end here. Thank you.
Great, thank you so much. Does anyone have any comments or questions?
Mike?
Hi. I see that the spectrum is 0559, which is famous, of course, for being very bright. I was wondering if you have multi-epoch data and any indication if the radial velocity might vary for this source.
So there's some slight variations, but we can't really see any obvious RV trend as a binary. So it could be due to inclination and other orbital factors, but we don't see a very common evidence for this source.
Derek?
Thanks. So I was almost just withdrawing my hand because it seemed like I was going to ask about the mechanisms in these offsets. Very instructive study anyway. Thank you. So thanks. It looks like the missing opacity is to make the lines too broad. That's forcing the fits towards lower gravity with narrower lines. And I was thinking that was contradicting the spurious rotational broadening, but I'm getting it right. I think that goes into the same direction. Have you looked into that? Would you agree?
So if I understand your question correctly, you mean there any correlation between the log G and V psi I? Yeah, we saw the trend, and this is also in the posterior, but like I don't have the plot right in hand, but there's a, so if you go to say lower log G, so for example, BDCL model, and you get like higher V psi, but if you go the opposite way, you can see the not the opposite way. So and the difference could be like in orders of few kilometers per second, maybe 2 or 3.
Serge?
Hi, Dino. This is, thanks for presenting this. This is really useful information. My question is that, do you have a sense if it happens at other temperatures or not, particularly higher temperatures? Is there a point where they diverge, or did you test just this particular object? Or
so I did like this plot just show the T2 surveys. I'm still working through the whole UCDs, but typically because I want to derive the precise RV and V psi, and I focus on in the earlier spectral type, I only focus on the order 33 in K band. So with the CO band head rotation vibrational transition, but I haven't really tested like other regions. And by the way, this model is with the tellurics, so I also add the telluric specs on that as well.
okay, a follow-up. Does it matter for the linear velocity as well? Do you find that there's more of a scatter in linear velocity?
So if you don't mask any missing line like these features, and you see some offset, but if you do the sigma clipping method, just to to max out some of the very deviated lines, and you get statistically consistent RVs still.
Okay.
So RVs is more robust, more constant parts of V psi I.
Thank you.
Yeah, sure.
Have you? I can't find the raise hand button. I apologize. This is Mark Marley again. Have you tried doing this at different wavelengths, because where you see different depths in the atmosphere? That would be interesting too.
So for J-band, I've tried. So because I want to again derive precise RVs, I only focus on the ones with the strong telluric features for wavelength calibration. So I've tried also order 57. That's also around the same wavelength, and also order 65, 66 in J-band, where you have potassium doublets as well. But I haven't really statistically tested if I see any other trends like that. Yeah.
Ben?
Hi there. Just a question about the gravity that you estimate on the Sonora model. It seems quite high at 5.5. I was just wondering, given the kind of the low radial velocity and I don't know the rest of the kinematics of this object, but is such a high gravity and the high implied mass for an object at this temperature kind of consistent with its kinematics, or is this another massive T-dwarf that we're running into?
So we don't really trust log G, because in this case, because we are only fitting a very like a narrow wavelength feature. But in my modeling parameters for both J and K band, with the orders I'm focusing on, usually it's sitting just on top of the log G. But if it's a binary and you see slightly like median, log G around maybe 4.5 to 4.8-ish. So, but typically we see it just hitting the end of the log G grid.
Going up to the top.
Great, thank you. I will end up obviously going a bit over time because we did start 15 minutes late, but I won't keep you any longer than that. So we have 2 more slides to get through. So next up is Mark, if you want to unmute yourself, if you're still with us. Great.
Sure. Yeah, thank you. Yes, I'm Mark Phillips. I've recently finished my PhD at the University of Exeter, and I did it on modeling cool brown dwarfs, generating a new 1D model grid. I have a talk tomorrow, so this is a shameless plug. I'm going to show most of my results in that talk. It's in the very low mass star section. For this slide, I thought I'd just quickly show some work that we've been working with, led by Sandy Leggett, who I believe is on this call, just on comparing some of our new models to the spectra of some new observations of late T and Y dwarfs. So I just show an example spectrum for a late T dwarf, which is in gray. We find that sort of a standard 1D cloudless radiative convective equilibrium model, we have departures, particularly in the Y and the J bands, they're too bright, which is well known. And at longer wavelengths, around 3 to 4 microns, the flux is way too faint, which is what's shown in these blue models. But by altering the pressure temperature profile, specifically by changing the adiabatic index, we can change the adiabat of the atmosphere, which changes the so the near infrared flux, it decreases it to match the observations a lot better. And higher up in the atmosphere, it warms the atmosphere around 3.3 microns to better match the longer wavelengths. So there can be quite a few different processes that can lead to these sort of non-adiabatic changes to the atmosphere. There can be breaking gravity waves in the upper atmosphere, which may do the heating in the upper atmosphere, and we may need some more heating in the upper atmosphere to get better matches to the data. And deeper in the atmosphere, so Pascal Tremblay has sort of suggested thermochemical instabilities as a way to decrease the temperature gradient. So this is a paper that's in review at the moment, and we show that this kind of works and can reproduce the spectral energy distribution of late T dwarfs into the Y dwarf regime as well. Yeah, so that was a quick summary, I guess.
Great, awesome. Do we have any comments, questions from anyone?
Daniela?
Yes, thank you. Hi, Mark. Thank you. This is super interesting. I'm curious about in the Y band, sort of shortward of 1 micron here, the blue spectrum, which I think is no cloud, fits a little better than the orange. The orange fits really well pretty much everywhere else, but like, could you comment on what could be going on those wavelengths?
Yeah, we generally have quite trouble in the Y band at low effective temperatures, and we think it's linked to potassium in some sense. Whether it's the line profiles, we have updated the line profiles, but again, there may be some errors left there. It could also be something to do with the rain out of potassium as it condenses into KCl. So here it looks like, at least in the blue spectrum, it's slightly warmer in the deeper atmosphere, which means there's slightly more potassium left over to match that wavelength region a bit better. So yeah, we have trouble with the potassium there, which we're not quite sure what's causing that, I guess.
And as a quick follow-up with that, does that potassium trouble trickle into a radius problem?
I don't think so. So I think the radii I use for these fits are consistent with evolutionary models.
Cool, thank you.
Do we have time for another question, Emily?
Yeah, one more question. Yeah.
Derek?
Okay, just quick one. What are the thick lines in your thermal profiles? Convective?
Oh, sorry. Yeah, it's the convective regions. So I completely missed that. But yeah.
All right, one last question.
Go ahead, Celine.
Your model, I think it's all solar metallicity. Do you plan to compute other metallicities, or it's not possible at the moment?
Yeah, so we're working on non-solar metallicities at the moment, both changing like the bulk metallicity and changing like the elemental abundances of, for example, carbon and oxygen. So it's in the pipeline, so they'll be coming soon.
Great.
All right, great. Thank you so much. Okay, and then on to our final slide. Last but not least, Adam, if you would like to unmute yourself.
Yeah, sure. And this is, there's not much really new here. It's just kind of a reminder when we're thinking about modeling that there are plenty of archives, spectral archives out there, including our own in SPLAT, the BDNYC archive. And Kelly mentioned on Slack the simple database that she's been leading the development of. So this is kind of a message for modelers, but also to remind all of us who, as we're thinking about how to compare the models, that there's a wide variety with many different physical properties. And to keep that in mind as we're sort of making increasingly more complex fits. So what I've shown on here is just a plot. I think I've shown like 1 million times in the last few years of just some of the different L3s we have in the SPLAT database and how they vary in age and vary in metallicity. And I'm personally still looking for a model that can capture a lot of these different factors self-consistently, and particularly with metallicity. So it kind of hangs on Celine's comment from before. And the other thing I wanted to just, I think again, as a message to the modelers is that the place where I feel we've still struggled for many years is understanding the LT transition and particularly modeling the spectra of the LT transition. We have lots of beautiful color magnitude diagrams that to some degree can reproduce the transition. And I know Pascal Tremblin has created these models that Mark just mentioned that has different adiabatic index. But even with one self-consistent set of models, it's often hard to reproduce consistently between the late L's and the mid T's. We're getting really good with the T dwarfs because I think mostly because the methane opacities have gotten better. But that phase where the clouds disappear is still really troubling. And we have lots and lots of spectra and lots of sources, thanks to Will Best, that we can follow up with these things. So, this is more of kind of a push for the folks who are doing developing the models. To really, if there's ways that we can kind of explore this in more detail spectroscopically, we've got plenty of data for it and plenty of sources that are benchmarks in this regime. So this is more of kind of a cheerleading for doing that effort.
John?
So I was sort of taken in the recent luminosity functions, and I mentioned this on Slack, but since Adam brings up the LT transition, it seems that the space densities also have a lot of information about the LT transition, but there's sort of different interpretations or emphasis in the recent papers. One by Will Best et al. And one by Davy Kirkpatrick et al. I wonder if Will or if someone from Davy's paper are online might comment on what they think they can learn from the luminosity function and the LT transition.
Go ahead, Will.
Happy to talk about things. I love the LT transition. I definitely would love to see more modeling of these spectra, which I know it's hard. In terms of the luminosity function, I think a big thing that we found in our study was that the progression across the LT transition in luminosity space and also in color space is not smooth. It's things slow up and they slow down and they speed up, and it must be an effect of the cloud clearing, or which relates to the release of energy from these objects, which I know the modelers think about all the time, and getting the prescription for that right I think is an absolutely key thing in the models. We looked particularly at the Sumner Marley 2008 hybrid model, which had in its prescription, it demonstrated that as objects moved across the LT transition, there was kind of a pile up in one place and a gap in another place. And we think that maybe they're sort of like the point at which that starts in, for example, effective temperature space may not have been quite right, but the idea was there. And we see that in our luminosity function as well. So that's a comment I could make. Does that answer something you're talking about, John?
Oh, I'm certainly happy, but I was just hoping to hear what people wanted to say. Sometimes there's more that we can say. Sometimes it's good to hear a conversation instead of just the
absolutely
written paper.
Yeah, I'll just add in that, Davey Kirkpatrick had a recent paper out, 2021 paper on the luminosity function, and he used the Simone models that always show this kind of weird, funny little bump right at the LT transition, and he's actually recovered that bump pretty well. So it does seem that there is exactly as we'll describe, kind of a funky transition that's happening here, a change in the evolutionary rate that's causing a pile up in numbers. Kelly, you have your hand raised. I don't know who calls on you, Kelly.
Well, I was just waiting because I wanted to appreciate the plug that you made for the simple database, and also to echo that one of the major motivators between the simple archive, I really want to call it an archive and not a database, is to facilitate modeling work. And so we have a couple folks who are involved who are planning to do retrievals with the observed spectra that we ingest. And we also want to ingest into the catalog the retrieved parameters. But if there are other folks who are primarily modeling, we'd love to work with you so that we're building something which integrates well into your workflow. And we're particularly thinking ahead to JWST and to the wealth of data which that is going to provide, and so that not everybody has to do their own data wrangling of this beautiful data set, and so that we can just facilitate the science getting done, and then we can take care of the data organizing. And so we really want this to be as open and involved of an effort now, so that we have a nice tool when the data starts to flow. Mike?
I wanted to add on this question that John raised. Everybody for a long time has been so fixated on the LT transition, which of course is really interesting, and gap and bump and who knows what's it. But if you actually stare at the data, just look at the data that's now available on the CMD, there are all kinds of other interesting features which are neglected, I think probably just as interesting. There's a huge agglomeration of mid-T dwarfs that occurs after the gap that hasn't really received very much attention. And there's all kinds of interesting, potentially fine scale structure in the L dwarf transition as well. And all these are, new diagnostics for what's happening in the atmospheres. We have, whatever it is, 1,000 or so objects with parallaxes now where we can do this. And I think the next big jump will come with LSST, where we can get parallaxes for many more things in the temperature ranges that we know about, but actually map out some of this fine scale structure much better. I think it'll be really, really interesting.
Great, thank you so much. All right, I think that feels like a nice time to wrap things up. So yeah, as I say, there is the Slack channel, so we can keep the discussion going, keep asking questions and bringing things out there. Thank you so much to everyone for participating, and for those that sent me slides. I enjoyed this. I hope this was useful to folks, and I hope that we can continue to chat about this. So
thanks for organizing, Emily.
Thank you, Emily.
We got there in the end.
Yeah.
Thank you for bearing with us.
No worries.
I'm also going to shout out to, we do have a low mass star Brown Dwarf dedicated Slack workspace, and John put a link in the Slack channel, but I think we should post it again so that we can use that one even after 20.5 is done.
Great, thank you. Awesome. All right, meeting adjourned, everyone.
Thanks, Emily.
Thank you.
See you, everyone.
Thank you.
Thank you. See you, everyone.
Thank you. Bye.
Thank you, Emily. Bye.
Bye.